This is one of the best subjects. If you want to be design engineers, this is mostly required for all the students. Very, very important subject for the mechanical engineering point of view. This is one of the best subjects for the mechanical engineers. Right? Let us see what does it have. Course objectives and other things. So after learning these things, you will be mainly knowing all the design principles, whatever the designing criteria, whatever design or formats or principles you have to follow, that you will be able to know. So what it is telling about, I'll tell one by one. After completion of this course, students will be able to solve the problems related to theory of elasticity, plane stress and plane strain problems, to study various isotropic materials and their relations, analyze dimensional problems, rectangular coordinates and polar coordinates. This is little bit of difficult for you. It will be having a lot of mathematics with polar coordinates and cylindrical coordinates. This is little bit of difficult one, third one. Actually, this is there actually in a master's level, but very little will be touching that analyzing dimensional problems in rectangular coordinates and polar coordinate system. This is requiring 100% mathematics, right? And fourth one, you can see find shear center for thin walled open sections, beams, etc. So what it is, this is also a very good level of mathematics. You have to know like lot of integral calculation will be there in fourth one. Integration will be there. And next one we have study theories of failure. That means we have like von Mises criteria, then maximum tensile stress, maximum tensile strain, all these things is there. Like maximum shear stress formula, these things will be there. So for designing, for engineers, this is must. Fifth one, if you don't know these things, you cannot go for design engineering. For designing engineering, the fifth one is must. Theories of failure. This is very, very important. The sixth one, what you have to know after completion of this one, you will be knowing the torsion theory of elliptical and square and rectangular cross-sectional objects. Seventh one will be understanding theory of viscoelastic material. And eighth one is apply Euler's and ranking formula to determine crippling load for various cross-sectional columns. These are the outcomes. After this completion of this course, you will be able to do these things. Let us see our contents in the next page. Content, what does it have here? First one, stress strain diagram.
Hello.
Yes. Hello.
Sorry to disturb you, sir, but there are some people who are trying to join.
Again. Okay. So you are there. The thing which we are discussing about the syllabus content. First one is stress strain. This is very simple. All of you have studied in engineering mechanics. Little bit of this one. Stress strain. This is very important one. And here you will be going through the most important part is actually principal stress and principal strain. This is very, very important from engineering point of view. Principal stresses and principal strain. And Mohs cycle, maybe you have studied this one, I don't know. This is also very important. That complex stress strain problem can be solved using this Mohs cycle diagram. This is very, very simple one. And all the mechanical engineers must be knowing this one. These two are very, very common for all the mechanical engineers. Principal stress strain and Mohs cycle representation. Second one is isotropic material. For the first chapter, we will be taking near about 5 to 6 lectures. It is written as 5, but we will be taking more than that. In every week, we are having total 3 lecture class and 2 hours practical class. So what is happening is practical class 2 hours will be concentrating more on mathematics, because practical class will be dedicating for solving assignments. And we are having total in this semester 8 assignments there. On each unit, we are having 1 assignment. And after completion of 1 unit, we have to submit the assignment. So from the beginning itself, you'll be assured that late, if you're submitting any assignment late, in that case, marks will be deducted. So we have to follow some specific format. If you're submitting late, so out of 10 marks, 2 marks will be deducted. So 2 marks for actually attendance, late attendance for your late submission of this coursework. So always you have to be assured that whenever the deadline is provided, you have to try to submit the assignments within that deadline. And here in this case, first one, we are having total 5 lectures, but it will be more than that. We will take minimum 6 lectures. 1 extra we will take because some chapters are there which is less. This one will take 6 lecture classes and 2 hours practical class. We'll consider these 2 hours as 1 hour will be your tutorial, that means we'll be solving numericals, and 1 hour we'll be doing your assignment works. This is our target. That is, within week we are having how much times? 3 plus 2, 5 hours we are having. 3 hours for your lecture class and 2 hours for practical one. Okay. Now isotopic materials also very small chapter. Here we are having theories of failure of isotopic materials. This is very small one, so we will continue. Material properties for isotopic materials and their relations. That means the relations between E, K, then mu, etc. You have to find the relations of all these things, and with these relations you have to find out mathematics. And theories of failures for isotopic materials we will not discuss here itself. We will discuss in some other class, because we are also having dedicated unit for theories of failures here in chapter 4. So these theories of failure will be concluding the remaining one and this one also. So what we are having in unit 2, theories of failure for isotopic materials, that one will be continuing in the 4th unit. The third one, what it is having? Third one is having a little bit complex things. In the higher level of mathematics will be there. That is two-dimensional problems in rectangular coordinate systems. This is completely mathematics, and this is mainly there in master's level. So we'll try to concentrate on very little applications of these things. So because it is having applications to polynomials in rectangular and coordinate systems and Saint-Venance principles. So we'll be concentrating less on this chapter because this is having completely mathematics, and we'll try to concentrate on maximum on our applications. Next to that, the very important part is theories of failure. This is very, very important. I told you at the beginning also, from the mechanical engineer's point of view, this is must. So here you can see von Mises criteria of failure is there. Tresca yield criteria is there. Different things there. Maximum normal stress is there. And together that will continue the previous one. What we didn't consider in theories of failure criteria here is there. So here it will be this one plus 3. Total 4 will be there. If excluding that, if anything is remaining, that one also will consider in theories of failure. Now, regarding theories of failure, you should know why it is so important. Because mainly when you are considering our stresses, strain, etc. on a object, so if we see what we have studied before, suppose this is object, this is one object. So you are providing one kind of stress, you are providing some kind of load here, you are providing some kind of load here. So let us drag it here. So I'll tell you why this is so important. That is your theories of failure criteria, why it is so important. Suppose you are applying some kind of load, that is your tensile load on any object. So directly you know how the stress will be. Stress will be your force per unit area, force divided by area. This is your stress. But the thing is, sometimes it may so happen when you are applying on the object not only this tensile stress, but maybe so including that one, some other things will be also included. Maybe your shearing stress will be also included. Maybe a bending stress will be also there. So different types of complex stresses will be involved. In that case, you don't know which one will be the formula, whether it is the actual for normal stresses, formula sigma equal to force upon area, that is equal to stress. Similarly, you know, like shear stress tau also is equal to force by area. But in that case, we have to understand the drawing or diagram, how it will be working. But when on any object, maybe shearing stress is there. When 2-3 different types of stresses are involved on any object, in that case, you have to follow, that is, what type of failure criteria you have to follow, whether it is von Mises one, Tresca one, or maximum one, or depending on material also you can see what type of failure theorem we have to follow. That one we'll discuss in detail later on. Now, next one we can see, or shear center. This is very, very important. 100% mathematics with your integration will be there. Integration. At this moment, you will not understand, but when we will discuss this thing in detail, you will understand. Shear center is very, very important. And here you will have all mathematics related to integration. Integral calculus will be there. You have to find out moment, then shear stress, etc. So here some complex mathematics will be also there. Right? This is very, very important. In master's level also, this chapter is there. Shear center. That means you have to find a location. Location means you have to apply a force. At which location, if you apply the force, the object will not be having any kind of rotation or moment. You cannot have any kind of rotation of this one. Suppose this is a plain paper. This is a plain paper. Plain paper. If you apply the load on this one, what will happen? This will try to bend. Some kind of rotation will be there, or bending will be there. So here also you have to find the location at this point, at which point you apply the force. The object will not be any kind of rotation or tilting or bending. That one you have to find out. That is shear center. Torsion, you already know what it is. Let us erase this one. Now torsion. Torsion, what it is? It will be having torsion of bars with elliptical and square and rectangular cross sections. Using membrane analogy, hydrologic dynamical analogy, torsion of hollow and thin tubes. Here some kind of numericals will be there, together some kind of formula derivation will be there. Derivation, and by the same time you have to do some kind of mathematics. Next one, it is theoretical. Lot of theories will be there, like viscoelastic properties and viscoelasticity. It is material properties, so material response regarding to viscoelastic material and linear viscoelasticity. These are the things actually. This is not that much of mathematicals. This is having a lot of theories. And last one is our this chapter. This is having a lot of mathematics. So you can consider this subject will be full of mathematics. And in all classes, you have to bring your calculators, because without calculators you cannot solve, because maximum classes will be doing only mathematics. The last chapter is actually loaded columns. So concept of critical loading and buckling, crippling, crushing stresses will be there, and Euler and Rankine theories will be there. And also we will be having slenderness ratio, safe load, etc., and Rankine's formula, etc. will be discussing. Regarding books, what we will be discussing? We have a lot of books, but best book here it is Timoshenko and Young. This is best book. This is the best book. You try to follow this one. Excluding that, we are having some other books. We can see what are the books to be followed in this case. First book it is Timoshenko Young. This is very important one, best book. Even when we were students also, we studied this one, Theory of Elasticity by Timoshenko and Young. And also some other books are the Khurmi. Khurmi is a very good one, but it is very easy. For the student's point of view, this Khurmi is very good one. Khurmi, maybe you can see these books are available as a soft copy also. You can have download this one from internet. R.S. Khurmi, this is one of the best books for the student's point of view. This is very simple, and the language what it has told is very clear and very easy language. R.S. Khurmi, very book, easy book. So we'll be following this one also. And if you want to go for higher things, that means you have to go for some books like Den Hartog. You can see whether it is there or not. Den Hartog. So it is having maximum application oriented things. The number 3. So this is very good book, Den Hartog. So here we will having lot of drawings or drawing diagrams. It is concerned about mainly your application oriented things. So these 3 are very good books. Excluding that, if you want to follow books which is following our syllabus, and also this is from Maharashtra, that person P.H. Jain. It is following some university from Mumbai, Maharashtra University, P.H. Jain. This is also good book. So these 4 are the best one. Other things, these are also you can see as a reference. So mainly we will be following, what are the things we will be following? We will be following Timoshenko and Young. That is mainly for theories of elasticity, and maximum times we will be following this R.S. Khurmi. And if you don't have that book, you don't worry about this, because this book is available in internet as a soft copy. You can get this one as a soft copy, and this one is very easy and very good for the student's point of view. So R.S. Khurmi, you take note this one. R.S. Khurmi is the best one for the students. Definitely it is available in internet as a soft copy. You can get it. So these are the books you can follow. This is for some specific portion for theory and elasticity. This is very good one, and mainly we will be concentrating on R.S. Khurmi. And if you want to do something like for your higher studies, if you want to know more for application oriented things, you can get Den Hartog book. This one I have already seen. This is a lot of mathematics with applications. So these are the things. So without wasting time, let us start our first chapter. What it is? Let's see. We have to start our first chapter. Let us erase all these things, and you can import that document from here. So first one is having 120 numbers of pages, 21 numbers of pages, slides. And here's a lot of mathematics are there, and this mathematics we will not be discussing. This mathematics I have converted into as your assignments, and we'll be doing some different types of mathematics here. And what it is given here, that types of mathematics will be solving in your assignment classes. First one, your solid mechanics. This is the first slide. What topics will be considering in first chapter? Let us see. The topics we'll be considering in a first chapter is types of stresses and strains. This one already you know. Again, we start with types of stresses and strains. What are these things? Hooke's law. Also, you know, you studied this one in lower classes. Working stress, lateral strain, etc. Poisson's ratio. This is one material property. This is actually unitless. Volumetric strain, etc. These things we will not study right now. Volumetric strain. Volumetric strain, actually all these things are there in second unit, and we'll touch this one, elastic modulus, and we'll not discuss everything in detail. Here we'll only touch these things, and detailed study of these things will be there in the second unit. Deformation of simple and compound bars under axial loading, that problems also will be doing. And next one is analysis of composite bars with varying cross-section areas. That type of problems also will do. Principal stresses and strains. This is most important part in this syllabus, in this chapter, or in from mechanical engineer's point of view. This is the most important part, that is principal stresses and strains. Then we have, let us see what is stress strain invariance and Mohr's circle. Mohr's circle, this is the easiest one. That means using graphs you can find out how much is the stress strain on any inclined plane or any complex object. Suppose if you're having different types of stresses or strains on a specific object, you can find out that maximum principal stress or maximum principal strain, whatever may be, using this Mohr cycle. This is very simple one. Okay, so let us start our first class now. So type of stresses, this one already you know what it is. Suppose this bar, this may be what type of section, maybe rectangular section or cross section, that is not an issue. One bar is there, and at the end of the other bar you are applying a force of F, and this part is fixed. So as you are applying a force of F at the other end, so what type of stress will be developed? Some kind of stress will be there, that is your tensile force. That means the length of the bar will be extended. When the length of the bar is extending, in that case the force is known as tensile force, and the stress developed inside the object is known as tensile stress. So the stress, actually you can denote this one in the by the form of, you can stress, this should be known as sigma. So this is sigma. When you are talking about stress, you should know this is sigma. Sigma means stress. Okay, so what I am talking about, that's direct stress. It may be tensile in nature, it may be compressive in nature also. Tensile means when the object will be trying to be elongated, length of the object will be more, in that case tensile stress will be there. But before that you should know what is stress. Directly you know that stress is what, in any body, if you are applying some kind of force, this is a body, if you are applying some kind of force, it may be force, may be tensile force, it may be compressive force, that is not an issue. When you are applying a force on a object, what will happen? The internal some kind of changes will be there inside the body. To balance that force, when you are applying the force, to balance that force, some kind of changes will be there inside the body. The body will be trying to like restrain that force. The body will be trying to counter attack those forces. So some kind of restraining force will be developed, that will, which will be trying to counter attack these forces. Some kind of restraining force will be developed, that is known as your restraint force. And if you apply that force, and you can see that force is applied on some specific areas. If you see this area, it may be circular, it may be rectangular area. So force divided by area will be your stress. Stress in this case will be equal to what amount of force you are applying, that is force divided by area. Now area, that is actually cross-sectional area. If you cut this one, you will be having area. It may be rectangular, it may be circular, depending on the object. That area is equal to A. Now, sometimes it may so happen you are trying to find out stresses on any plane which is not perpendicular to the force. Here the force is perpendicular to these cross-sectional areas. That is known as the normal force or normal stress. When you are applying a force in this direction and the cross-sectional area is perpendicular to that one, that means you are finding a stress on that object. That stress is known as normal stress. It is denoted by sigma n, normal stress, right? Okay. Now sometimes it may so happen you can have that stress on an inclined plane. That one also will do, that will do later on. Now you know that here what we are doing on any object, if we are applying a force, then inside the body some kind of restraining force will be developed, and that restraining force divided by the area is known as your stress, right? Now the force what you are applying on the body, it may be your tensile force. Tensile force means what? When the body is trying to be elongated by the application of force, if the length of the object is increased, then that force is known as your tensile force. If the object is trying to be shortened, in that case the force is known as your compressive force, and the stress developed will be your compressive stress. Let us see what it is. So stress, you know, stress is when you are applying a force on any object, inside the body some kind of restraining force will be developed. The restraining force per unit cross-sectional area is known as your stress. The cross-sectional area, if it is perpendicular to the direction of force applied, then it is known as normal force. Normal force or normal stress. Sigma n it will be represented by. Next page you can see what it is. Stress, the formula is equal to O force by area. Force is equal to restraining force, and area is what? Area is known as your cross-sectional areas. Now very important thing, that means in your any kind of interviews, when you will be attending any kind of interviews, definitely they will be asking the unit of this one. Unit of stress is what? Unit of stress equal to Newton per meter square. Ultimately you can tell is this one is Pascal. Pascal. And if you see the unit of pressure is what? Pressure is also equal to force upon area. Pressure is also equal to force upon area. Let us write this one with this highlighter. Pressure equal to force upon area. Now I can ask you something. Pressure is also force per unit area, and your stress, that is also force per unit area. So what is the difference in between these two? Can anyone tell what is the difference between these two? Pressure is equal to force upon area. Unit is also Pascal. Unit is Pascal. Newton per meter square Pascal. What is the unit of sigma? That is also Pascal. Both case unit is same. Formula is also same. But what is the difference, main difference between pressure and your sigma? Can anyone tell what is the difference? Sarang Chaudhuri? Anybody? Do you have any idea about what type of difference we are having for stress and strain?
Stress is the resistance offered by the body, but pressure is the force applied on the body.
I didn't understand it. Can you repeat this one again?
Actually, stress is about the resistance of the body, sir.
Okay.
But this pressure, it is the force applied on the body.
It is okay, but 100% I'm not confused. It's okay. Can anybody?
Just
It
right,
is okay.
sir.
Anybody can tell anything extra? Because from this one also we can have some kind of like MCQs also. Definitely some MCQs will be there between this pressure and your stress. Dinesh, can you tell this one?
Sir, as like Parvendra said, stress is just a resistance of the body, but strain is
Not
changing.
strain. No, not I'm asking about strain. I'm asking pressure and stress, the difference. Remember what is told is perfect, but I want to add something extra.
No, sir,
Not strain.
I thought it was about stress and strain.
No. Pressure. I'm talking about pressure and stress. Both are having same formula. Pressure equal to force upon area. Stress is also upon force upon area. It is restraining force. This is also force, but unit is also same. In both cases, you are having unit equal to Pascal. Okay. So the difference at this moment you will not understand. I will tell you the difference, but you will understand the difference when I will talk about some kind of graphs. I will draw some stress strain curve. Then your idea will be 100% perfect from this one. Okay. What is infinite amount of values will be there for pressure, but stress, it is having some specific values. After that, this pressure, this sigma is not having any meaning. That means I want to tell that sigma or stress is an internal property. As Purnanda told, it is a restraining force. It is an internal property, but pressure is external property. Maybe it is not clear to you, but within a very short time, I'll explain this one with a specific drawing or specific diagram that is known as stress strain curve. Try to understand in your examination also, sometimes in Viva it will be asked, stress is the internal property and your pressure is external one. So on any body, if you apply more force, as the force is increasing, your pressure will be also increasing. So infinite amount of force you can apply, the pressure will be also variable, pressure will be changing. But after certain limit, the stress is having no meaning. If we apply more force, sigma will be increasing, sigma will be increasing again and again. But after some time, this is having no meaning. That one I'll explain within a very short time. Okay, next to that slide, the strain. This one also you know, strain is what? Strain is equal to two types of strain will be there. When you are applying some kind of load on any object, so the object will be having increase in length. If we are applying tensile force, that means the load will be trying to make the object to be elongated. Length of the object will be more. In that case, some kind of strain will be developed. Strain is what? Strain is equal to change in length divided by original length. But here in this case, suppose I want to draw one drawing. Let us see one drawing with highlighter. This is one drawing we are making. We are applying some kind of tensile force. That means object will be trying to be elongated. Length will be more, right? Length will be more. Now, when you are trying to make the object to be elongated by the application of force, the length will be increased. But what about the diameter of this one? What about the diameter? Definitely, volume will be actually what? Your mass will be constant. Mass will not be changing, right? Volume is also what? Volume is also, as you see, mass equal to volume into density. Volume is, if density is not changing, so mass equal to what? Mass equal to volume into density. V into D. V into density, right? Now, as you can see, is the length is increasing. That means volume. If volume is constant, then this diameter. This is not diameter. This is density. We are talking about something. This is density. Now, if you don't consider these things, if you apply the tensile force on that object, the length of the object will be increased. But at the same time, the diameter of this one will be decreased. Right? Diameter will be decreased. Now, as you are applying the force along the axial direction, along this direction, so there will be increase of length. So length of increase is equal to, suppose represented by del L, and original length of the object was suppose L. In that case, the strain is equal to, strain is represented by epsilon. This is epsilon, that is known as strain. Strain is equal to change in length, that means how much increase or decrease it is happening by the application of tensile force. Definitely it will be some kind of increase. So strain is equal to increase in length divided by original length. So definitely this is length by length. This is a dimensionless parameter. It is not having any kind of unit. So remember this one, strain is a dimensionless parameter. It is not having any unit. Strain is also two different types of strains are there. Let us hear this. So strain, when you are applying force in the axial direction, at the direction of force, along the direction of force, there will be some kind of increase in length or maybe some decrease in length. If the force is tensile, in that case, length will be increased. If the force is compressive, that means length of the object will be decreased. In that case also, we can have some kind of decrease in length. So strain will be how much? Strain will be a change in length per unit length. It is unitless, no unit is there. But as the length of the object is increasing by the application of force in the direction of force itself, it is known as longitudinal strain. Along the direction of force, if the length is increasing, that type of strain is known as longitudinal strain. Now, the opposite thing also can happen. As I told, if we are applying force in the direction of force along this direction, but opposite direction perpendicular to this direction, what will happen? The direction of this one along this direction, diameter of this one will be decreasing. So there also you can have some kind of strain. That strain will be actually your what? Lateral strain. Right? Different size of stress as lateral strain, longitudinal strain. Strain is what? Strain, it may be your lateral also, along the direction also, it may be perpendicular direction also. If you see perpendicular direction, it will be decrease in diameter. So it will be decrease in diameter, del D divided by original diameter. That is your lateral strain. Right? This is also epsilon 1, that is your strain, and this is also strain. But these two are different. This is actually along a direction perpendicular to the direction of force, and this is along the direction of force. Lateral strain and longitudinal strain. Okay. So next to that, we can go something else. Let us see what is there. Okay. Now, some kind of relationship there. For getting mathematical relations, we have to find some mathematical relations for stress, strain, etc. As I told that before getting these relations, I have to go for some kind of drawings that is known as stress strain curve. Before going to these things, let us tell about stress strain curve. Now, I'll talk about little bit of experiment. Let us talk about some kind of experiment. Let us talk about some kind of experiment at this moment. What it is regarding your stress strain curve. Suppose we are having one object here. This is one graph regarding stress and strain. This is very, very important from engineering point of view. This is a object, and we are applying some kind of force here. This is definitely tensile force. We are applying force, and this is having cross-sectional area equal to A. Now, what will be happening? So we'll try to increase the force one by one. So we'll plot force, stress and strain will be developed when you are applying a force on any object. The object is having cross-sectional area equal to A, and we are applying a force, suppose F1, F2, F3, F4, etc. We have different types of force we are applying on that object. Suppose initial force we are applying on the object equal to F1. So as we are applying force F1 on the object, so in that object some kind of stresses will be developed. The stress equal to sigma 1. Sigma 1 equal to how much? Sigma 1 equal to F1 divided by A. Force F1 divided by A. Initially you will see the area will not be changing that much. Very small changes in area will be there. As we are applying the force, change of area will be very, very less initially. Right? Change of area will be very less initially. When you are applying a force of F1, the object will be having some kind of stress, that is equal to sigma 1. By the same time, some kind of strain will be also developed. Strain is equal to, suppose, epsilon 1. So epsilon 1 is developed by the application of force F1. Right? Epsilon 1 will be how much? Will be equal to change in length. Suppose by the application of force 1, the object is having a length of change equal to del L1. Del L1, that is change of length by the application of force F1, and original length is L. So this is the first change in length per unit length, that is known as strain. So by the application of force F1, we got stress 1 sigma 1 F1 by A, and strain epsilon 1 equal to del L1 by L. Again, what we do? Again, we increase the force F2. Second time we applied a force. In this case, we have applied a force equal to F1. Right? Okay. Next case, what we did? Next case, we applied a force of F2. In that case, what will happen? Sigma 2 will be developed. If we apply a force of F2, sigma 2 will be developed. That is equal to F2 upon area. Because I told that initially the change in area will be very, very less. Actually, change in area we can see when it's about to be fractured, then only that area will be properly visible. Initially, you cannot see that much of changes area. So by the application of force F2, again epsilon will be created, that is known as your strain. Epsilon 2, that is equal to again del L2. Del L2 divided by L. Del L2. Del L2 is what? That is changing length of that body by the application of force F2. Again, original length will be unchanged. So by this way, you are doing again and again, we are changing this thing again and again force we are changing again and again. F1, F2, F3, F4, etc. We are applying. Maybe at last moment what we got some another force. Before we are doing this thing till the object is fracturing, we are applying the force F1, F2, F3, F4, etc. And here the force is equal to F2. Here we have applied a force of equal to F2. Now these things are going on till the object is breaking. So F2, F3, F4, F5, etc. we are applying. So suppose the object is breaking at the force when the force is Fn. The fracture is occurring. So by the fracture force Fn, let the sigma develop known as sigma n. That is stress n equal to how much? So it will be before fracture. This is actually before fracture. Okay, see, equal to Fn. We applied a force of Fn divided by A. So A, I told beginning. So change of A is very small, negligible. So we are considering this is approximately equal to A. Similarly, by the application of Fn, when the force is very high, in that case your epsilon will be also very high. That will be suppose epsilon n. By the application of force Fn. So that will be how much? That will be del ln. Del means change. Del ln divided by L. Right? We got a different values of sigma 1, sigma 2, sigma 3, sigma 4, etc. And similarly, we got epsilon 1, epsilon 2, epsilon 3, etc. We got lot of things. Now what we'll do is, with all these things, what we'll do, with all these things, we have to plot. What we'll do, we got different values of F1, sigma 1, sigma 2, sigma 3, sigma n, epsilon 1, epsilon 2, epsilon n. Now with these things, what we have to do, we have to plot. We have to plot one graph. So how to plot these graphs? We have to plot a graph along this one. Suppose this is the axis. You see, this is the axis. Suppose this is one axis and this is another axis. Two axes are there. Now along this axis, along this y-axis, we will be plotting. What we will do, along this x-axis and y-axis, we will be plotting something. Along y-axis, we will be plotting stress sigma. So that one we can erase. Along this one, we will be plotting sigma. Okay, let's start this one with highlighter. This one will be sigma, and along this axis, we will be plotting what? Epsilon. That means your strain. Right? If you plot at a specific value, this will be suppose 10 Newton. This one will be some 0.001, whatever it may be. So if the sigma 1 and epsilon 1 plotting along y-axis, it will be sigma, along x-axis, it will be epsilon. If you plot these things, you will see a lot of graphs, a lot of points will be there, a lot of points will be developed. This 1 point, 1 point, 1 point, these are the different points. If you join these points, what will happen? You'll see this type of graphs will be developed. So again, see, these are the points. Okay, so what we did, we have plotted defined values of sigma and defined values of epsilon based on defined values of forces. Initially, we applied a force of F1, then we got sigma 1 and epsilon 1 that we plotted. This is epsilon 1, along this one, this is epsilon 1, along this one is sigma 1. So this way we plotted defined values of sigma and epsilon. After plotting these things, if you connect all these things, suppose we are connecting these things. So if you connect these things, you will see a straight line will be developed here at this point. Some kind of straight line will be there. So if you connect these things, it's not perfect. It will be like that only, right? It will be like that. If you connect these things, you'll get a curve. This is known as stress strain curve. Now, very important to understand this part. This is very important to understand. You must have to understand this one. If you understand this one, so maybe from design point of view, your basis will be clear. So this curve you can explain and you can break into two different regions. First region, you can say when we're applying, you can see this is actually near about straight line. If you see, this is approximately a straight line up to certain limit. Up to certain limit, when you're plotting these things, you can see this approximately equal to line, straight line. So this region is known as your,
Sir, Purendra is trying
okay,
to connect, sir.
this is elastic region. Punanda, what is he talking about? So what I was talking about, see, up to certain limit you can see it will be a straight line. So this region is known as elastic region. The left hand side, this part is known as elastic region, and the right part is known as plastic region. Now this is having too much of importance, these things. Now if you plot different types of materials, different types of graphs will be getting. Now up to certain limit, suppose inside that object, this is the object, you have applied a load of F1. In that object, you have applied a load of F1. Suppose 10 Newton force you have applied. Now if you remove the force, it may so happen the object will come back to its original position. It will be working as a spring up to certain limit. Up to certain limit of force, if you are applying a force, F1, F2, F3, F4, etc., up to certain limit, up to this limit, the force, the object will be working as an elastic body. Try to understand what I am talking about. If your force is increasing, so up to certain limit, the object will be working as an elastic body. If we remove the force, object will come back to its original position. That is known as elasticity or elastic property of that object. So it will be straight line. Up to that point, this is known as elastic point. This up to this point, you can say stress and strain is directly proportional. Up to that point, sigma is directly proportional to strain. Stress is directly proportional to strain up to that point. Right, up to that point, when it is a straight line, this is known as your stress and strain is directly proportional. And to remove this proportionality constant, proportionality sign, we have to apply one constant. Suppose stress is proportional to strain, and to get a formula from this one, we have to apply a constant. Right. Suppose I'll give one example. Suppose my age and your age is proportional. As my age is increasing, your age is also increasing. But if you want to get my actual age, what you have to do? If you want to get your actual age, you have to multiply this one with some constant, right? As my age is increasing, your age is also increasing. So directly proportionality symbol is there. If you want to get a constant relation, if you want to get the actual values, some constant should be multiplied. So similarly here also, stress is directly proportional to strain up to certain limit, up to elastic limit. So that constant should be known as E. Sigma is equal to E multiplied by epsilon. E multiplied by epsilon. Right. So E is equal to how much? E equal to sigma upon epsilon. That is actually, you can say, one constant, that is modulus of elasticity. Right. Equal to sigma by that one. Okay. Now what I am talking about, for different materials, these types of things will be different. So up to this limit, you can say, for designing anything, when you are going for any designing, this should be your maximum one. That means your yield stress, sigma y. This point is known as sigma y, yield stress. That means up to this one, your stress is safe. After that one, if you apply a force, object will be having plastic deformation. This is plastic deformation. That means permanent deformation will be taking place. The object shape will be deformed completely. It cannot come back to its original position. I'll repeat this one again. So up to certain amount of force, if you are increasing the amount of force F1, F2, F3, F4, etc., it may so happen that up to certain limit, if you remove the force, object will come back to its original position or original shape. That force is known as safe force, or the stress developed inside that object, that is known as your safe stress. And the maximum safe stress is known as yield stress. That is denoted by sigma y, yield stress. But that is not the maximum one. If you see in the graph, this is not the maximum. Maximum one is some point here itself. That is known as ultimate stress. Because our aim was that in that experiment, what we did, we have increased the amount of force F1, F2, F3, F4, etc. At different amount of forces, we have plotted stresses and strains. Up to certain limit, we observe that when stress is increasing, strain is also increasing with a specific proportion. That proportion is sigma is directly proportional to strain, and that proportionality will be replaced by a constant that is known as your Hooke's law. Hooke's law is what? Stress is directly proportional to strain up to a certain limit. That is up to a elastic limit. That elastic limit is point. This is, suppose this point is A. Up to that point, that stress. Here up to that point we applied a force, suppose F y, yield force. Suppose we applied a force that is equal to Fy. Then stress developed will be how much? Sigma y. That sigma y is equal to, for design point of view, this is the maximum stress can be applied on an object to have a safe body or safe object. If you apply a force on that object, if the stress is more than this yield stress, then that object, the object will not be safe, because in that case plastic deformation will be occurring. Plastic deformation means the object, if you remove the force, object will not come back to its original position or original shape. Object's shape will be completely deformed. That is known as plastic deformation. Now for different types of material, this type of drawings will be different. This is for ductile material. Ductile means what? Ability to undergo large permanent deformation and by the application of tensile force. Ductile material, some definitions are there. So as a MCQ also, it may be asked in your viva or in your questions, in your examinations. What is ductility? Ductility is a property by virtue of which the material undergoes large permanent deformation under tension. If you apply a tensile force, the object will be undergoing large permanent deformation, because you can see deformation is there up to this one, some deformation, but this is elastic deformation. So this is a ductile material. Suppose aluminium. If you see aluminium, this type of behavior you can see. If you plot stress strain curve, you can see this type of behavior will be there. This is ductile in nature. Behavior is there. So what is initially you will see there is elastic behavior. So if you remove the force, object will be coming back to its original position. That is elasticity or elastic force, or you can say elastic region. And after that, if you apply the force, force will be increased. By the same time, your stress will also increase. This is the maximum stress. This is known as ultimate stress, sigma u. This stress is known as sigma u or sigma ultimate. And this sigma is known as sigma yield. Yield stress is a maximum safe stress, right? And this is ultimate stress. And this is your rupture stress or failure stress. Failure, when the fracture will be occurring here. Now, if you plot different types of material, so you will get different types of drawings in this case. Now, today up to this one we will be concluding. Next day we will continue this one with for different types of materials. So you have to understand this one, that maximum stress for safe designing, you have to follow yield stress, and this is your ultimate. Ultimate is actually not safe for your design point of view. This one you cannot see. For design thing, you have to consider this yield stress only. And sometimes you can know that factor of safety. What is this? So these things also we'll consider in the next class. Okay. So up to this one we'll conclude. Let us erase these things. Let us go back to our presentation things. So I'll take your attendance right now. Okay, you can leave right now. Up to this one is okay for you. And tomorrow we are having some practical class. This will be 2 hours class. That in that class we'll be doing a lot of mathematics. Okay, so you can leave right now. I'll take your attendance now. Okay, all of you can leave right now at this moment. So we have time 45 minutes. Maybe we are having next class. So
Thank you, sir.
okay, thank you. Attendance already downloaded. Now let us close our recording.